Hey everybody, so we're going to pick up now in section 4.4. Just want to make sure you guys can see that, and you can't. Okay, so 4.4, laws of logs. Last section we covered the basic definition of log, which was used as an inverse to the exponential function. Here, what we're going to learn to do is combine and expand log expressions, right? Now there are a few rules that we can use to help us manipulate terms. Almost everything that we saw last time had, let's just say, one expression. If I had to do log to the base 2 of 16, which asks us to evaluate 2 to what power would equal 16, right? Here, in this section, what we're going to be exposed to is a few different rules that allow us to manipulate expressions like, well, what would happen if I had log to the base 2 of 16 plus log to the base 2 of 4? What would we do there? We have two log terms. Well, this would be asking us 2 to what power gives us 16. So the exponent here is the 4th power. And this says 2 to what power gives me 4? The answer is 2. And 4 plus 2 is 6. So there should be a way that would allow us to say combine these two terms. This obviously gets a bit more challenging when we're dealing with variables as opposed to just numbers. So we're going to see, and as you see on slide 78 within section 4.4, there are three main rules that are listed. What are those rules and what do they mean? Rule 1, log to the base a of ab. Now ab is a product, a times b. Log to the base a of a times b is going to equal log to the base a of a plus log to the base a of b. What this means is if I have the log of a product, I can break up that product and take the separate log of each one of the two factors. So if I had the log to the base 7 of 3x, I could break that up to log to the base 7 of 3 plus log to the base 7 of x. That's what that rule allows me to do. Now, it doesn't necessarily mean that log to the base 7 of 3 can be evaluated cleanly. 7 to what power gives me a 3? It's not really so cut and paste, cut and dry. But we'll see when this is somewhat useful, especially within some of your practice problems. You're going to be using this theory here to be able to break up a term or a factor, let's say, and you can maybe potentially take the log to that base of each one of the individual factors. It would be easier to do that. It's also important to note, by the way, that these rules don't just work forward, they also work reverse. So if I were to see that log to the base 7 of 3 plus log to the base 7 of x, working in this direction is called expanding. Working in the reverse direction, so if I was given this term, I can combine the terms because they have the same base, and I could say that's equal to log to the base 7 of 3x. That's called combining. And this is going to be true of the next two rules that we see as well. Not only will you be able to expand, you will be able to combine expressions as well, depending on which direction you work it, forward or reverse. And again, these rules are going to be meant to help us work out specific problems that we're going to see in the following slide. Rule number 2 says log to the base a of a quotient, a over b, is equal to log to the base a of the numerator minus log to base a of the denominator. And again, we're going to see this in action, but if I have the log of a quotient, I can then just bring it out to be the log of the numerator minus the log of the denominator. One way is expanding, the reverse way is combining. The third rule, log to the base a of a to the c power. So if I have any value to a power, what I can do is represent it as c times the log of a. Essentially take the power out of the parentheses and multiply the log of a times the value of that power. This one's going to be really important to us. Not that any of the other ones are not important, but the third one is going to be super important when we're trying to solve exponential and logarithmic equations. We'll see why and how within 4.5. But again, all three of these rules are very useful in helping us evaluate log expressions. We're going to go to slide 79 now, the next slide, to see some examples. Slide 79. So example number 1. If you use the laws to expand the log, so if I were to ask you to expand log to the base 5 of x cubed y to the 6th, how would you manage that log expansion? Well, do it in a couple of steps. First one, I see that there's a product here, x to the 3rd, y to the 6th. So I'm going to write this as log to the base 5 of x to the 3rd plus log to the base 5 of y to the 6th. Next, I'm going to bring down the power. I'm going to rewrite this as 3 times the log to the base 5 of x plus 6 times the log to the base 5 of y. So first I used rule 1 to break up the product of the two factors within one log expression to be the sum of two log expressions. That was rule number 1 that we used. And then I used the third rule to bring the exponents down, to say, hey look, we have a constant as a power. Based on rule number 3, log to the base, log of a to the c can be c times log of a. So I'm going to bring the 3 out front and say I have 3 times the log to the base 5 of x, and then bring the 6 down front and say 6 times log to the base 5 of y. And that's a fully expanded form of the initial term. We had to do 2 steps to fully expand the first term. Next, the ln of ab over the cube root of c. Here we see something a bit more involved. Now, again, just because we see ln and not log, it doesn't mean that we can't do the same math. Remember, ln means log to the base e, right? That's what ln means. It's the natural log. We spoke about this in 4.3. So when I see ln of this term and I want to expand it, I can write it as the ln of ab, because that's the numerator, minus the ln of the cube root of c, because that's the denominator. So I use rule 2 to break up the fraction. The ln of a times b, then I use rule 1. So first I use rule 2, now I'm going to use rule 1. Rule 1 says that the log of a product is the log of the first factor plus the log of the second factor. So first I use rule 2, say I have ln of AB minus ln of the cube root of C. Then I take this one and I say, hey, I can simplify this and expand it out further, because that's a product, and by rule 1, the log of a product can be rewritten as the log of the first term plus the log of the second term. Here also, oddly enough, or interestingly enough, we can simplify the cube root of C. If you remember way back when, the cube root of C we could also represent as C to the 1/3 power. So if I rewrite my radical expressions in rational form with exponents, you'll see that you can substitute and then also expand out these terms further, which is how your textbook does it and web work as well. So ln of the cube root of C will have 1/3 times the ln of C, because this is really C to the 1/3 power, and the third rule, or rule number 3, allows us to bring the 1/3 down. So this term is the final answer. Combining log expressions. So the first example with combining log expressions, I had another example 1, but this is now combining, it's working in reverse. Log to the base 2 of 80 minus log to the base 2 of 5. So I have a minus here and the bases are the same. That allows me to use rule 2 in reverse. That gives me log to the base 2 of 80 over 5. 80 divided by 5 is 16. Log to the base 2 of 16. And log to the base 2 of 16 is 2 to what power is 16? The answer is 4. So unlike here and here where my answers are left in variable form, this one I could actually evaluate. Whereas if you gave me log to the base 2 of 80, 2 to what power gives you 80, you wouldn't really be able to solve for that. 2 to what power gives you 5, you really wouldn't be able to solve for that either. So the second one, 2 ln of 5 plus 1/3 of the ln of x. Here we have a constant in front of the log term. If we use the reverse of rule 3, we'll see here that we get the ln of 5 squared plus the ln of x to the 1/3. If we use rule 3 in reverse. Since it's a plus, that'll give us the ln of 25 x to the 1/3. And you can leave it in that format. Some of you can rearrange that to be the cube root of x. It really doesn't matter to me. But that would be your final answer in condensed form. So instead of expanding, like the first 2 problems, these last 2 problems combined. The last thing on the section, they discuss change of base formulas. So not everybody has the latest graphing calculator, which will allow you to evaluate things like log to the base 2 of 80, right? So in the newest calculators, you could actually go into a specific functionality. Once you turn these guys on, you can go to math, this button right here, and then you'll see, if you scroll up, not down, second to last function says log base. When you hit that, you have a log to the box of a box. So I could literally put in log to the base 2 of 80. And I can evaluate that on the newer calculators. Get a 6.312. On the older calculators, like the 83 pluses, you can't really do that. But there's a way around it. You can use the change of base formula, which is on slide 79. So the formula will say log to the base b of x can be rewritten as log to the base a of x over log to the base a of b. What does this mean and why is it so useful? Basically what this is telling us is that regardless of the base that I have, I can turn this log function into a fraction with a log in the numerator and denominator. As long as those two logs have the same base, we're okay. So if I have log to the base, and let's use a live example. Log to the base 9 of 20, or I have log to the base 8 of 5. Technically, you can change this to be log to the base 10 of 5 over log to the base 10 of 8. Why? Why is this so important? Who cares that I can change it to log to the base 10 of 5? 10 to what power gives me 5? It still doesn't make sense. I still can't find 10 to some power that gives me 5. It does make sense though. Because any calculator can do log to the base 10. Every calculator has a common log function. We discussed that on the last iteration, right? Log. The log function in your regular calculator is log to the base 10. So if I can change any problem to log to the base 10, then I can use any calculator to solve it. I don't need some special functionality on my calculator. I can just go into a calculator and hit log 5, because this is the common log. I don't even have to write 10. I can do log 5 over log 8. Log 5 divided by log 8. You get 0.77. Or you can change it to log to the base e 5 over log to the base e 8, which is the natural log. That's the ln of 5 over the ln of 8. Will you get the same answer? Let's test it. ln of 5 divided by the ln of 8. Remember, as long as the base in the numerator and denominator are the same, you should be okay. ln of 5 close parentheses divided by the ln of 8 close parentheses. You still get 0.77397, so you get the same answer. Make sure you use the parentheses to close off the logs. So if you did log of 5 over log of 8, or ln of 5 over ln of 8, you'll get the same answer as log to the base 8 of 5. They're all equivalent. Okay? So it doesn't matter the type of calculator that you have. As long as you can use a change of base formula, you can manipulate any log expression and either change it to a base of e or a base of 10. And I think we're done for 4.4. Stay tuned for 4.5.